Welcome you all for this video demonstration. In this video, I am going to demonstrate the sampling of given analog signal and different types of sampling using MATLAB software. Before going to start the simulation of this MATLAB, let us know the necessity of sampling process. Always the signal available in the environment is analog in nature. Example, voice signal, music signal, image signal and video signal, etc. Nowadays, processing of these signals are carried out in digital domain. So we want to convert these signals into digital signal before processing. So first step in analog to digital converter is the sampling process. This will convert continuous time signals into discrete time signal. Sampling is applicable only for a band limited signal. There is a condition for selecting a sampling frequency. So for band limited signal, in order to reconstruct the signal exactly, the sampling frequency is greater than or equal to twice that of fundamental frequency. Minimum sampling rate required, it is called as Nyquist rate. So let us see the simulation in MATLAB. So first we are going to clear the command window, then clear all the files, all the figure windows open related to this MATLAB programming. So then generate the analog signals. So for generation of analog signals, we need a fundamental frequency. Then from that fundamental frequency, we are calculating fundamental period t equal to 1 by fm. So then we are fix the range for time index. It's vary from 0 to 5 cycles, 5 times t. Then specify the step increment between each sample values. So then in this I am generating the analog signal as sinusoidal signal. We know that the sinusoidal signal is having a functional form. It is sine of 2 pi fm into t. So x equal to sine of 2 pi fm into t. So for each and every time index value, this will calculate the amplitude of sinusoidal signal. So once the amplitude of sinusoidal signal is calculated for each time index, so then display that signal using a plot command. So subplot, it is used to divide the figure windows into m rows, n columns, and third value it is indicate the which position you are going to display the output. So in this program, I am going to show 5 waveforms in a single figure window. So that's why I selected it's 2, 3. So it will divide the figure windows into 2 rows and 3 columns. And in the first position, I am going to display the analog signal. So analog signal is a continuous in nature. That's why I am using a plot command, plot of t, x. So it will display the generated waveform in graphical. So I want to label that waveform, x label and y label, and I want to give a title for that waveform using this inbuilt command. So x label is time and y label is amplitude, and this waveform indicates the analog signal. So once this analog signal is generated, so now I'll simulate this waveform. So this is an analog signal, it is generated using MATLAB. It's a sinusoidal signal with 5 cycles of waveform it is generated. Then after generating your sinusoidal signal, so then you want to perform a sampling for this signal. So sampling is nothing but we are doing a slicing of that signal at every sampling instant. So I am selecting sampling instant as 2 sample. So every 2 sample the signal is sliced. So this is a command we are using for sampling. So I am selecting only that every second sample from analog signal, and it is stored in XS. So now the sampled signal I want to display it. For that I am using a stem command because it's a discrete signal. So this stem command, it is used to display the signal in discrete form. So this waveform, it is displayed in the second portion in the figure window. So for this signal also I am going to label that signal. X-axis is N, Y-axis is amplitude, and title is a sampled signal. So now I am executing these two signals. So in the figure window, first portion the analog signal is displayed, and second part it is a sampled version of this signal. So let us see the different types of sampling based on your sampling frequency. So there is undersampling, critical sampling, and oversampling. So in undersampling, so we are fixing the sampling frequency is less than 2 FM. So for this program I selected as sampling frequency is equal to FM. So for this sampling instant, so we are going to sample your signal. So I will fix a time index 0 to 5 cycles of your sinusoidal waveform we are generating it. So but the sampling instant for this signal, it is fixed as 1 by fs1. For every fs1 this signal is sampled. So then calculate the amplitude value sine of 2 pi fm into n, and this is a undersampled signal. X1 equal to a sine of 2 pi fm into n. So in this the sampling interval, it is fixed here, it is 1 by fs1. So fs1 is nothing but fm. So once it is undersampled signal is generated, now you display the signal using a stem command, and I am labeling it x-axis, y-axis, and title of this waveform is undersampled signal. Then critical sampling. In critical sampling, the sampling frequency is selected, it is twice that of the fundamental frequency. So now you assign a range for n time index, that is 0:1 by fs2 is a sampling interval, it is used for this case, and the same 5 cycles of the sinusoidal signal is generated. So for each and every value of n, next calculate the amplitude of this signal. So then display that signal using a discrete stem command. Then label it. This is a critical sample. So next it is an oversampling. The sampling frequency here I selected, it's greater than 2 FM. So I'll fix a value is 10 times that's fundamental frequency of the signal. So for this sampling instant, now I am going to sample the signals. So now assign the range for n 0 to 5 cycles of sinusoidal waveform. The sampling interval, it is 1 by fs3. Next calculate the amplitude for this range. Each and every value of n, the amplitude is calculated, then it is displayed. This is a oversampling signal. So now I am going to simulate the entire program, sampling and different types of sampling. So I am getting it. So first waveform is an analog signal, then this is a sampled version of the signal, then this is a undersampling. We are selecting your sampling frequency is less than 2 FM. For this program, the sampling frequency is fixed as FM. So next category is a critical sampling. Fs is equal to 2 twice that of fundamental frequency. So we are getting a sampled version of the signal as this. Then it is an oversampling signal. Fs is fixed as greater than 2 FM. So we are getting this waveform. So from that simulated output, so we are going to do analysis. So if you done undersampling, the signal nature it is not reconstructed at the receiving side. It does not follow the nature of your original signal. So it creates the aliasing effect at the receiving side. We are not able to reconstruct if you perform a undersampling. Then in critical sampling, somewhat the nature of the signal we are getting it. But if you select a sampling frequency is greater than 2 FM, so we get exact nature of your signal after sampling. So at the receiving side, if you perform a oversampling, we can reconstruct the signal exactly. So this is described in the sampling theorem. If you select a sampling frequency is greater than 2 FM, so we are able to reconstruct the signal exactly at the receiving side. But if you select undersampling, we are not able to reconstruct the signal at the receiving side. That creates the aliasing effect. So that's all about your sampling process and different types of sampling. It is simulated in the MATLAB.